Hello, good morning everyone. I am V. Suriya, Assistant Professor, Adiamon College of Engineering and Technology, Department of ECE. I am going to go do a video lecture on electromagnetic fields. Uh, Electromagnetic force is nothing but a Lorentz force. It is given by physics scientist Hendrik Anton Lorentz. The equation of Lorentz force is F is equal to Q into E plus U cross B. The Lorentz force equation is quite useful in determining the paths charged particles will take as they move through electric and magnetic field. If you also know the particle mass m, the force is related to acceleration by the equation F is equal to ma. The first term in the Lorentz equation represents the electric force Fe acting on a charge q with an electric field is given by Fe is equal to Qe. The electric field is in the direction of electric field. Magnetic force. The second term in the Lorentz force equation represents magnetic force Fm of n on a moving charge q is given by Fm is equal to q into u cross b, where u is the velocity of the charge in meter per second within a field of magnetic flux density b. The units are confirmed by using the equivalences. Weber is equal to volt into second and joule is equal to newton into meter, that is equal to coulomb into volt. The magnetic force is at right angle to magnetic field. The magnetic force requires that the charged particle is to be in motion. It should be noted that since the magnetic force acts in a direction normal to the particle velocity, the acceleration is normal to the velocity and the magnitude of the velocity vector is unaffected. Since the magnetic force is at right angle to magnetic field, the work done by the magnetic field is given by the formula W is equal to integral over force into the differential length. Here it will become force into dl cos 90 degree. So since cos 90 is 0, it will be equal to 0. Magnetic force on a current element. Consider a line conducting current in the presence of a magnetic field. We wish to find the resulting force on line. We can look at a small differential segment dq of a charge moving with a velocity u, and we can calculate the differential force on this charge by using the equation df is equal to dq into u cross b. The velocity can be written as u is equal to dl by dt. By substituting the velocity equation, df is equal to dq into dl by dt into b. Now, since dq by dt is in coulomb per second corresponds to the current I in the line, we have df is equal to I into dl cross b. We can use this to find the force from a collection of current element using an integral. So, the total force in the current element is given as F12 is equal to integral over I2 dl2 into B1. Magnetic force of infinite current element. Let us consider a line of current I in the AZ direction on Z axis. For current element IDL, we have IDL is equal to IDL into AZ, where AZ is the unit vector in the direction of Z axis. The force is given as dF is equal to IDL in cross B, where B is the magnetic flux density for an infinite line of current. The magnetic flux density H is given as I by 2 pi rho, whereas the magnetic field intensity B is equal to mu naught into H1. We can represent B is equal to mu naught I by 2 pi rho into A phi. We know this element produces magnetic field, but the field cannot exert magnetic force on the element producing it. As an analogy, consider that the electric field of a point charge can exert no electric force on itself. What about the field from a second current element IDLB on this line? From Biot-Savart law, we see that the cross product in this particular case will be 0, since IDL and AR will be in the same direction. So we can say that a straight line of current exerts no magnetic force on itself. Magnetic force of two current element. Now let us consider a second line of current parallel to first. The force dF12 from the magnetic field of line 1 acting on a differential section of line 2 is dF12 is equal to I2 into dL2 cross B1. The magnetic flux density B1 for an infinite length of current is recalled from equation B1 is equal to mu naught I1 by 2 pi rho into A phi. From that we can say rho is equal to y and A phi is equal to minus of Ax. That's just opposite to the direction of x axis. Inserting this in the above equation and considering that dl2 is equal to dz into as, the big equation of force becomes F12 is equal to mu naught I1 I2 divided by 2 pi y of minus ay integral over dz. To find the total force on a length L of line 2 from the field of line 1, we must integrate df from plus L to 0. We are integrating in this direction to account for the direction of the current. We will get F12 is equal to mu naught I1 I2 into L 2 pi y into ay. This gives us a repulsive force. Here F1, F21, the magnetic force acting on line 1 from field of line 2, we would have found that will be the negative of F12. So F21 will be equal to minus of F12. From this we can conclude that two parallel lines with current in opposite direction experiences a force of repulsion. For a pair of parallel lines with current in same direction, a force of attraction would result. Magnetic, in this more general case where the two lines are not parallel or not straight, we could use the Biot-Savart law to find the magnetic flux density. The equation is given as below. This is known as Ampere's law of force between a pair of current element carrying circuits and is analogous to Coulomb's law of force between a pair of charges. So next topic is magnetic material and boundary conditions. We know that current through a coil of wire will produce a magnetic field akin to that of a bar magnet. We also know that we can greatly enhance the field by wrapping the iron around an iron core. The iron is considered as a magnetic material since it can influence. In this case, we can amplify the magnetic field. The degree to which a material can influence the magnetic field is given by the relative permittivity mu r, analogous to relative permittivity epsilon r for dielectrics. In free space, a vacuum mu r will be equal to 1 and there is no effect of the field. The magnetic material can be divided into three types: diamagnetic, paramagnetic and ferromagnetic. The tabular column shows the materials, types of diamagnetic, paramagnetic and ferromagnetic and respective permeability. Magnetic flux density. In presence of external magnetic fields, a magnetic material gets magnetized. This property is referred to as magnetization and it is denoted as M. M is equal to chi m into H, where psi is the magnetic susceptibility. The total magnetic flux inside the magnetic material, including the effect of magnetization in the presence of external magnetic field H, can be written as B is equal to mu naught H plus mu naught M. Substituting m is equal to psi m into h, we will get b is equal to mu naught into 1 plus psi m into h. That will be equal to mu into h, where mu is 1 plus psi m and mu is the material's permeability related to the free space permittivity by the factor mu r called the relative permeability. Magnetic boundary condition. We can calculate the magnetic boundary condition using Ampere's circuit law and Gauss law to derive normal and tangential boundary condition for magnetostatics. From Ampere's circuit law, we know that closed integral over h dot dl is equal to I. I is the current enclosed. Here the picture shows that we consider a boundary medium 1 and medium 2, where medium 1 the relative permittivity is mu 1 and medium 2 is mu 2, and we are going to consider a rectangular path in which we are going to find the magnetic boundary condition. The current enclosed by the path is I is equal to integral over k into dw. By integrating it, we will get del w. We can break up the circulation of h into 4 integrals. The closed integral over h dot dl will be equal to a to b in plus b to c plus c to d and d to a of h dot dl. We will get equal to k into del omega. In part 1, a to b of h dot dl will be equal to a to del omega 0 to del omega h tangential into the unit vector AT into the differential length dl and unit vector AT. So we will get ht1 into del omega. For path 2 we will get minus hn1 plus hn2 into del h by 2. For path 3 we will get minus ht tangential 2 into del w. For path 4 we will get hn1 plus hn2 into del h by 2. Here del w is the width and del h is the height. Now combining our result, we will obtain the closed path of integration over h dot dl will be equal to k into del omega. From tangential boundary condition, ht1 minus ht2 will be equal to k. A more general expression for the first magnetic boundary condition can be written as a vector a21, that is unit vector of 21 into h1 minus h2 will be equal to k. A21 is the unit vector normal going from media 2 to media 1. Special case, if the surface current density is 0, if k is equal to 0, we will get h tangential 1 medium 1 will be equal to ht2. The tangential magnetic field intensity is continuous across the boundary when the surface current density is 0. We know that B is equal to mu naught mu r into h. From this we can obtain h is equal to B by mu naught mu r. So we can written as in terms of B, Bt1 by mu naught mu 1 equal to Bt2 by mu naught mu 2. So therefore we can say that Bt1 will not be equal to Bt2. The tangential component of magnetic flux density B is not continuous across the boundary, but magnetic field intensity is continuous across the boundary. From Gauss law, we are going to find the magnetostatic field. Integral over B dot ds is equal to 0. To find the secondary boundary condition, we center a Gaussian pillbox across the interface. We can shrink del h such that flux out of the side of the pillbox is negligible. Then we have closed integral over B dot ds is equal to B normal component an into ds an plus B normal component 2 in an into ds of minus an. So we will get bn1 minus bn2 into del s will be equal to 0. That will be represent bn1 is equal to bn2. Normal boundary condition is bn1 will equal to be bn2. Thus we see that normal component of the magnetic flux density must be continuous across the boundary. We know that B is equal to mu naught mu r by h. From above equation we infer that hn1 will not be equal to n2. The normal component of magnetic field intensity is not continuous, but magnetic flux density is continuous. Thank you.